To install a specific version of the numpy library in Python, you can use the command that specifies the desired version, like in this case where version 1.19.5 is being installed. Executing this command instructs the package manager, pip, to fetch and install the indicated version of the numpy library. This command is useful when a particular version of a library is needed for a project to guarantee that the code performs as intended. By selecting a specific version, you can ensure consistency and compatibility across various projects or systems, as different versions of a library might contain distinct features, bug fixes, or changes in functionality. Mounting Google Drive to a Colab notebook allows easy access to files and directories stored in Google Drive. This simplifies handling data by enabling direct operations on files without manual uploads or downloads. This feature is valuable for tasks involving large datasets or intricate file structures, enhancing workflow efficiency. This script is designed to manage directories within a designated project directory structure. It starts by importing required modules such as OS and path from the pathlib library. The script begins by setting a base directory path using path, which is commonly used for working with file system paths. It then creates the full project directory path by combining the folder and project_dir with the base path. By using os.chdr, the script changes the current working directory to the project path and proceeds to iterate through all items in the project directory. For each item in the project directory, the script verifies if it is a directory by using as_dir. If the item is a directory, the script retrieves the directory name relative to the project path and then renames it. In this scenario, each directory name is separated by a space, and only the first part before the space is retained as the new directory name. Upon completing the renaming process for all directories, the script displays the current working directory using os.getCwd. This script is utilized for automating the renaming of directories within a specific project directory structure based on a defined rule or condition. It facilitates batch renaming of directories, allowing for the organization or cleanup of directory names to align with a particular naming convention or standard. To get the specified version, 2.0.0, of the TensorFlow library with GPU support, you can use the Python package manager pip. TensorFlow is a widely used open-source machine learning framework created by Google. The GPU version enhances the library by utilizing the parallel processing capabilities of GPUs, which speeds up the training of neural networks and various machine learning models. Installing particular versions of libraries guarantees consistent operation across various environments and dependencies. This snippet accomplishes several important tasks. 1. Importing essential modules and libraries such as Ipython, Pandas, OS, Time, Glob, for data handling, visualization, and deep learning using TensorFlow. 2. Ensuring forward compatibility by utilizing features from the __future__ module to make the code compatible with upcoming Python versions. 3. Importing a CSV file into a Pandas dataframe to analyze financial data from the specified file. 4. Verifying the version of TensorFlow in use and checking if the system supports GPU for faster computations. Using this code is crucial because it sets up the environment by importing necessary libraries and enabling essential features. It loads financial data into a dataframe for analysis purposes. It verifies TensorFlow compatibility and GPU availability, significant for efficient deep learning computations and faster model training on compatible hardware. The preprocess function processes data from a list of CSV files as follows. 1. It initializes lists data 0, data 1, data 2, and data 3 to store values from specific columns in the CSV files. 2. It loops through each file in the all_files list. 3. For each file, it reads the contents using the CSV module. 4. It skips the header row in each CSV file. 5. It extracts values from columns 1 to 4 of each row, converts them to floating point numbers while replacing commas with dots, and adds them to the respective lists. 6. It creates a numpy array named data with dimensions, number of rows, 4, and stores the processed data in it. 7. It displays the processed data along with its shape. 8. Finally, it returns the processed data as a numpy array containing floating point numbers. This function facilitates the efficient reading and preprocessing of data from multiple CSV files, ensuring that string values are converted to floating point numbers and that the processed data is stored in a structured numpy array for further analysis or manipulation. Its automation streamlines the process, making it more organized and effective. This text discusses a script dealing with financial data. 1. The variable data_dir equals financial_data, data, indicates the base directory where financial data is located. 2. The glob function retrieves file paths matching a specified pattern. It returns a list of file paths for files in the tron, val, and test directories within the base directory. 3. The path join function constructs full file paths by combining the base directory with specific subdirectories, tron, val, test. 4. The preprocess function likely preprocesses the loaded data, which may involve tasks like reading data, cleaning, normalization, and feature extraction. 5. The preprocessed data is stored in variables train_data, val_data, and test_data, each containing preprocessed data for the training, validation, and test sets, respectively. This code facilitates loading and preprocessing financial data from various directories within the specified base directory. Preprocessing is crucial for preparing data for modeling or analysis, ensuring it is suitable for machine learning algorithms or other analytical processes. This text provides information about the shapes of different datasets: train_data, val_data, and test_data. The dimensions, rows, columns, of the train_data dataset can be obtained using train_data shape. This information helps to understand the dataset's size and structure. After displaying the shape of train_data, the code proceeds to show the entire contents of train_data, followed by presenting the shapes of val_data and test_data. This code is useful for monitoring the data in a machine learning project, ensuring that datasets are loaded correctly with the expected dimensions. It also aids in identifying issues like missing data or data loading errors. This segment is used to plot a specific portion of the train_data array. The explanation of each part of the code is as follows. 1. Initial variables. The code sets start to 0 and dt to 5999 for further use. 2. Creating array k. An array k is created with 5999 numbers generated using NP linspace. 3. Manipulating train_data. The code flips train_data vertically, takes a slice from start to start plus dt along the first axis, and flips the resulting slice along the first axis. 4. Plotting the data. It plots the selected portion of train_data using plt plot with y-axis values from the first column of train_data. X-axis is labeled as time delta and y-axis as index. 5. Displaying the plot. The plot is displayed using plt show. This code visualizes a specific subset of train_data to observe data patterns or trends. Flipping the data and plotting a segment can aid in understanding the dataset better or revealing hidden patterns. The graph provides insights into the data's trends and behavior over the specified time range. This text discusses cubic spline interpolation applied to a portion of the train_data array. The SPLEP function creates a cubic spline representation, while the SPLEV function evaluates this spline at specific x1 values. Cubic spline interpolation is a technique used to estimate intermediate function values at given points using known data. It involves creating a piecewise polynomial function that smoothly passes through data points with continuous first and second derivatives. This interpolation method is widely used in signal processing, data analysis, and numerical methods to estimate values between data points. Cubic splines offer a more continuous and smoother curve than linear interpolation, making them valuable for visualizing and analyzing datasets. This text describes a series of tasks related to signal processing or spectral analysis. 1. Calculating the length of a signal using the len function. 2. Determining the frequency resolution df based on the sampling frequency fs and the signal length nfft. 3. Creating an array K2 ranging from 0 to nfft1 using np. A range, nfft. 4. Calculating the frequency values f for each index of K2 by multiplying K2 by df. 5. Calculating nfft_half, which is half of the length of nfft using math. Trunc. 6. Extracting the positive half of the frequency values from the f array and storing it in f0. 7. Performing fast Fourier transform, FFT, on a signal y1, normalizing it, and extracting the positive half of the FFT values, storing it in FFT_y0. 8. Calculating the amplitude spectrum by taking the absolute value of the FFT values of the positive half and storing it in amp. These calculations are essential in signal processing for analyzing signal frequency content. The output is typically used for further analysis or visualization to understand the frequency components present in the signal. This snippet initially verifies if the condition true holds true. If it does, it proceeds to generate a new figure and axis by calling plt subplots, with a specified size of 20 by 10 inches. Next, it plots a graph using plt plot, by utilizing the f0 and amp data. Finally, it showcases the plot by invoking plt show. This code snippet is employed to create a plot and exhibit it. It is a common practice in data visualization tasks to represent data visually for analysis. The plt subplots function is utilized to form the plotting figure and designate its dimensions. Subsequently, the plt plot function is applied to plot the data on the figure. Lastly, plt show is used to present the plot on the screen. This script likely belongs to a Python program utilizing numpy (np). It carries out the following steps. 1. Sorts amplitudes in descending order using np argsort amp, where amp likely holds amplitude values. 2. Iterates through the top 10 elements of the sorted amp array using for I in range 10. 3. Prints the frequency and amplitude values corresponding to these 10 elements by indexing f0 and fft_y arrays with sort c I. The code aims to extract and display the frequencies f0 array and amplitudes fft_y array of the top 10 largest amplitudes. This process is commonly employed in signal processing, data analysis, or scientific computing to identify the most prominent components in a dataset by sorting the amplitudes for easy identification of frequencies with the highest amplitudes. This segment initializes three empty lists r_freq, r_coits, and r_cos, and a zero array NUI with the shape, nfft. Then, it iterates through a range of 20 elements, from 0 to 19, extracting frequency, real part, and imaginary part of data located at sorted indices from arrays f0 and fft_y, storing them in respective lists r_freq, r_coits, and r_cos. It then plots two traces from arrays k and train_data, start plus dt, 0, in red labeled as original, and from x1 and NUI in blue labeled as fft. The resulting plot is displayed using plt show. This code processes and visualizes FFT, fast Fourier transform, data by extracting specific results and comparing original data with FFT data. It helps in analyzing the frequency domain representation of a signal or dataset, offering insight into underlying characteristics and patterns. This process involves manipulating a data frame that contains stock market data in the following steps. 1. Selecting specific columns, date, end, open, high, low, from the original data frame. 2. Making a duplicate of the selected data. 3. Modifying the date column by removing any non-numeric characters, nyon, wal, il, spaces, and converting it to an integer. 4. Modifying the end, open, high, and low columns by removing commas and converting the values to floating point numbers. 5. Reversing the order of rows in the data frame and resetting the index. This code aims to clean and format the stock market data to facilitate further analysis or processing. Data cleaning is essential in data analysis to maintain accuracy in calculations and avoid errors during subsequent data manipulation tasks. This snippet demonstrates how to create a plot using the matplotlib library in Python. Here is a breakdown of its functionality. 1. Creating a figure and subplots with a specified size of 12 by 6 inches. 2. Retrieving the current axes object within the figure. 3. Plotting data from a dataframe on the y-axis against the dataframe's index on the x-axis, specifically using the values in the end column. 4. Displaying the plot on the screen. This code is valuable for visualizing data, aiding in the identification of patterns and trends within the dataset. It finds applications in data analysis, scientific research, and various other fields that rely on effective data visualization. The FFT function defined in this program performs a fast Fourier transform, FFT, and inverse FFT on a specified column of a dataframe. Here is the breakdown of the process. 1. The FFT function computes the FFT of the input data column using np.fft.fft. 2. It then zeroes out a specified number of values in the FFT array, which can be helpful for filtering or denoising by eliminating certain frequency components. 3. Next, the function calculates the inverse FFT of the modified FFT array using np.fft. Ift. 4. The function returns the real values resulting from the inverse FFT. The code applies this FFT function to the end column of the dataframe FFT_df with a parameter of 50, top n equals 50, and stores the result in a new column labeled FFT 50. Additionally, it creates two more columns, denoised and denoised_img, which extract the real and imaginary parts of the FFT 50 column through lambda functions. Lastly, the code displays the first few rows of the resulting dataframe FFT_df, showcasing the original data, FFT results, and denoised components. This code is beneficial for signal processing tasks, allowing the analysis of data frequencies and noise removal using FFT-based denoising methods. This text describes a process of plotting the end and denoised columns from a dataframe, FFT_df, onto the same graph. The plot size is specified as 30 by 15 units. It starts by creating a figure and axis with a specific size. Then, it retrieves the current axis. Next, it plots the end column from the dataframe on the current axis and then plots the denoised column on the same axis. Finally, it shows the plot. This code is used to compare and visualize the relationship between the end and denoised columns in the dataframe. The plots aid in understanding how the denoised data differs from the original end data and help in identifying patterns, anomalies, or other insights within the data. This text describes the process of scaling selected columns, end, open, high, low, denoised, in a dataframe using the min-max scaling technique. Here's a summary of the steps involved. 1. Import the MinMaxScaler class from the preprocessing module of the escalern library. 2. Create an instance of the MinMaxScaler class. 3. Define the columns to be scaled, end, open, high, low, denoised. 4. Apply the scaling transformation to the specified columns using the fit_transform method of the MinMaxScaler object. 5. Convert the scaled data into a dataframe. 6. Rename the columns of the scaled dataframe to match the original column names. 7. Convert the dataframe into a numpy array. Scaling is crucial in machine learning to normalize features to the same scale, preventing any one feature from dominating the model. Min-max scaling standardizes the data within a fixed range, typically 0 to 1, enhancing the performance of certain machine learning models and algorithms, particularly those sensitive to variable scaling like SVM, k-nearest neighbors, etc. An autoencoder is a type of neural network designed to learn efficient representations of the input data. The network consists of an encoder that compresses the input data into a lower dimensional representation, and a decoder that reconstructs the original input from this representation. In this implementation, 1. The encoder model is defined with 3 dense layers in a sequential neural network. It takes a 5-dimensional input and outputs a 2-dimensional representation of the input data. 2. The decoder model is also defined with 3 dense layers in a sequential neural network. It takes the 2-dimensional representation from the encoder and outputs a 5-dimensional reconstruction of the original input data. 3. An autoencoder model is created by connecting the encoder and decoder models in a sequential manner. The activation functions, ReLU for hidden layers and none for the final layer, and the number of nodes in each layer can be adjusted based on the specific problem and data characteristics. This autoencoder can be trained on a dataset to learn the compressed representation of the input data for tasks like data denoising, dimensionality reduction, or anomaly detection. Compiling a model in TensorFlow involves setting up the optimizer, loss function, and metrics that will be used to train the model. In this autoencoder model compilation, the optimizer set is Atom with a learning rate of 0.001, known for its good performance and efficiency in training neural networks. The chosen loss function is mean squared error, MSE, commonly used for regression problems to assess the average squared difference between predicted and actual values. The evaluation metric during training is mean squared error, MSE, to gauge the model's performance. This text describes the process of training an autoencoder model on a scaled dataset using the fit method. The autoencoder is trained to reconstruct its input data by encoding it into a lower dimensional representation and then decoding it back. The goal is to learn a compressed representation of the input data. Training an autoencoder involves defining the model architecture, compiling it with appropriate loss functions and optimizers, and fitting it on the data. Through training, the model learns parameters that minimize reconstruction error, improving the representation of the data. The fit method iteratively updates the autoencoder's weights and biases based on input and target data over multiple epochs to enhance its ability to reconstruct data accurately. In this case, the training is set for 50 epochs with a batch size of 50. Meaning the model processes 50 samples at a time before updating weights. This training process is important for tasks like data denoising, dimensionality reduction, or anomaly detection, as it helps the autoencoder learn an efficient representation of the input data. The performance of an autoencoder model is being evaluated by comparing its predictions with the original input data. The model is evaluated using the evaluate method on a specific dataset, df_scaled. The evaluation involves comparing the input data with the reconstructed output from the model, obtained by passing the input data through the model. Setting verbose equals 2 controls the display of evaluation progress, with a verbosity level of 2 showing results after each epoch. The evaluation results, which include loss and mean squared error values on the df_scaled dataset, are stored in the variable test_scores. The code then formats and prints the test loss and mean squared error percentage based on the evaluation results. This evaluation method helps assess how accurately the autoencoder model reconstructs input data and provides insights into its performance quality. Understanding the model's ability to encode and decode data accurately is essential for evaluating and enhancing its performance.